Welcome. Hello, everyone. I'm Dan Powers, Executive Director of the Society for Science at User Research Facilities. We are starting another session as part of our 2022 annual meeting, and we're going to be hearing today from Steve Kirby, who is the Project Director for the Advanced Photon Source Upgrade Project at Argonne National Laboratory. Before Steve comes on to start his presentation, let me give a little bit of background as to his topic here. The upgrade at the APS is really going to be building on something that is already quite a powerful facility. The ultrabright X-rays that the Advanced Photon Source generates are used by more than 5,500 scientists each year to create stronger materials and build more efficient batteries and help develop vaccines and treatments for infectious diseases, a spectrum of different types of applications for the research and the data that they're able to compile there. And now the upgrade is going to be a comprehensive improvement to the facility's electron storage ring, and it's scheduled to begin in April 2023. So Steve is going to be describing what has been happening with that project and really what the outlook and the aspirations are for the technology that Argonne is going to be launching into this next level of incredible capacity. Jim, I'm going to give you a little background on him, and you can bring Jim up onto the screen here. As I mentioned, he's the project director for the Advanced Photon Source Upgrade, and he oversees the planning, the construction, and the implementation of the upgrade. He joined Argonne in 2012 as the principal project manager of APS, the upgrade project, and later transitioned to chief project manager and has over 30 years of engineering and technical management experience. Prior to joining Argonne, Jim worked at Fermi National Accelerator Laboratory, including leadership of the $200 million US LHC Accelerator project. So with that little bit of brief background, please, Jim, you can add in any additional context that you would like the audience to know, but let me hand this over to you, and we're definitely interested to hear what's happening with the APS upgrade.
Thank you very much, Dan, for the introduction. I think I'll skip over anything else you might be interested about myself and get to the upgrade, which is the point of this. Thank you very much. It's a pleasure being here, and it's a pleasure to be able to talk about the project, which in fact, although we're getting started in final preparations for the upcoming shutdown, the reality is the project's been going on for a decade. It's what I joined the laboratory here to work on. And I'm happy to talk about it. So hopefully you see this in full screen mode at this point, right? So the transition, Dan mentioned what the upgrade and what the APS currently does, and we're upgrading the facility after it's been operating since 1996, actually. And part of the changes for the beamlines are already ongoing. And so what you see here is one beamline that's actually being moved from 20ID. It's an insertion device beamline. 20ID is one of our sectors. It's got moved 5 sectors over to make way for the next beamline to be installed in 20ID. So the upgrade's coming, and it's happening in real time. Dan mentioned this. DOE, the Department of Energy, actually operates 5 light sources in the United States. The APS is in the upper left here at Argonne National Laboratory. There are 2 at SLAC LCLS, which is currently being upgraded to LCLS 2. There's also SSRL, Brookhaven has NSLS 2, and the ALS, Advanced Light Source at Lawrence Berkeley Lab, which is also undergoing an upgrade, the ALS upgrade. And at a future time, you can hear about these. So this is the suite of facilities in the United States. There are several others in the Western Hemisphere, including the Canadian Light Source in Sirius and Brazil, among others. But the APS is the only high energy X-ray source, synchrotron source in the Western Hemisphere. It's larger than the other 2 and provides X-rays at higher energies that allow us to penetrate into ceramics and metals that a little more than the other facilities can. It is a mature facility. It's fully built out, as you'll see in an upcoming picture. Typically, in a unique year, we have in a normal year, we have 5,500 unique users from all 50 states and around the world. In a typical year, you'll see in statistics, last year was a bit lower than this as far as visitors due to COVID and ongoing effects with travel. There are 6,000 experiments per year. There are 2,000 high-impact publications per year, and the societal impacts of all of the light sources, including the APS, are really countless. The change from high-energy physics for me at Fermilab to the APS at Argonne is the difference between both are wonderful research institutions, but truly any of these light source experiments produce impacts on a weekly or monthly basis that advance society, and it's really really a benefit and a privilege to be able to work here. The Advanced Photon Source today, as mentioned, is 68. It's one facility, but there's 68 simultaneously operating experimental stations. So you can think of one huge facility, but in some ways we're providing X-rays to 68 separate experiments, sort of 68 dentist chairs, people have explained it, except the X-rays being supplied, of course, are a billion times brighter than you would get in a dentist chair. The APS operates 24 hours a day, 6 days a week for 9 months of the year, and there's a one-day maintenance period every week and 3 longer planned shutdowns that occur across the course of the year. In 2022, here are the numbers for this past year. There's 4,500 users, 580 institutions. So of those 4,500 users, only about 200 are from Argonne itself. This has always been a user facility, and Argonne has always worked as a facility that welcomed others to use what we have for the benefit of the nation and the world. There's a large industrial presence, and in fact, when we count users, those tend to be underrepresented in the counts, because industrial facilities, companies tend to have one resident user, and then they send all their samples to that particular user, as opposed to a university, which might have multiple grad students each bringing their own samples. And again, the experiment and the publication counts for the past year. You can see the color coding here sort of goes by the disciplines that we serve, and you can see on the next how those users map across those disciplines. In material science and engineering and chemistry are some of the largest ones. Somewhat underrepresented here are the medical applications and things that would go more towards drug discovery. There's actually a very large community that does drug discovery, but again, because of the way we count the users, those tend to be underrepresented in these sorts of counts, but they're of course critical to overall success. A couple examples of what the facility currently does and points of emphasis to us. Argonne has a large footprint in battery development. And of course, with cars and all sorts of other green energy generation things like wind power or solar power, you're looking for ways to store energy. And so there's a huge effort here on better batteries, improving the energy density storage, and also the types of chemicals used there. And the APS allows looking within the battery to look at that chemical reaction in real time, such that you can design a better battery for the future. The APS also had a huge impact on the COVID-19 research and the development of drugs, and also directly Paxlovid, which is data that was collected at INCACAT. This is a collaborative access team with an industry at the APS. And so that drug development and the speed with which that drug development was undertaken was directly benefited by the research here at the APS. Fundamentally, what it does is any light source, what it does is it allows the exploration of molecules at the atomic scale. So you're understanding the chemical composition of every molecule. And if you understand that, for drugs, you look at ways that you can develop something that fits that molecule to destroy it or to at least inhibit it. And that's what happens in drug discovery. For previous ones like the battery, you're looking again at how that chemical reaction occurs and how you make a better battery. So it's had an amazing amount of impact over the past 26 years. It continues to have impact these days, and we have an incredible user community that, again, continues to use this facility and wants to use it in the future. After 25 years, however, 26 years, you might imagine there could be some improvements made. The improvements over the past 25 years have been incremental to the facility. And however, much like your cell phone or anything else, technology has changed in the past 25 years. And so starting in 2012, actually, but then with the approval, the fundamental approval from the Department of Energy in 2018 and then 2019, the APS upgrade really got going. It's an $815 million project. We reuse $1.5 billion of infrastructure here at the existing facility. So if this had been built as a greenfield, this would have been a $2.5 billion project or something, but there's much of the facility that we can reuse. So it's an economical way to increase the brightness that's delivered to some of the beamlines by a factor of 500. It's the equivalent of walking into a what you think is a pitch dark room to one where all the lights are turned on. That's on many rooms a factor of 100 if you happen to measure it. So we're looking at making the beams incredibly brighter, 2 orders of magnitude brighter, and this opens up all sorts of new experiments that we can't do now, maybe not because we're simply not capable of doing them, or they would take so long that it's not practical to do them. So by increasing the data rates, and one of the advantages here at Argonne is we happen to have a supercomputer on the other side of site, we can lock in all the data that we're taking, the rates with which we're taking the data to that computer and use that computing power to reduce the data and develop what the next test is in real time. And so the upgrade is really taking advantage of other things going on here at Argonne to really leverage this for our user community in the future. The current progress in the past decade, it's been a lot of work, but this machine, essentially, we're approaching a dark time starting next year in the spring, and I'll talk a little bit more about that. But it's time for us to actually turn off the current facility, which we have to do carefully, because we want our user community both to do as many experiments as possible, but also come back when we turn back on in the shortest possible time. And you can see some of the pictures here. I'll touch on some of these, but we're completely replacing the storage ring. The 1.1 kilometer circumference storage ring, all the current magnets come out. It's a completely new lattice, which is the magnetic design for control of the electron beam the whole way around. And that requires new magnets. We have almost every one of those magnets on site, and you can see we're doing pre-assembly into things. The first new beamline instrument is up and running. Actually, there's 2 up and running now. The transition from the electrons to the X-rays. Now, the electron source storage ring is just a source to generate X-rays. X-rays are, of course, what our users want to do their explorations and their experiments. And so the transition is something we call a front-end system. And it's typically an insertion device or a bending magnet. And then we use a front-end system to collimate those X-rays to make sure they're being delivered safely to our experimenters. And finally, the long beamline building. You'll see in an upcoming slide the footprint of the APS. We haven't changed the footprint of the facility with the exception of 2 beamlines. And because of the scientific needs of those beamlines, the in-situ nanoprobe and the high-energy X-ray microscope, so Hexam and ISN, we have actually extended the footprint of the facility out to beamlines of length of 150 and 200 meters, as opposed to the current ones, which start to have a limit around 40 meters or so. All right. The project scope, the $815 million, the official DOE end date is March of 2026, but we're trying to do that as fast as possible to deliver this to our community. We replace and renew the whole facility. We're not so much replacing the outside walls, but almost all of the technical equipment inside the walls is being replaced. It's about half on the electron side of the house, the source, the storage ring, while the other half of the funds go to building and rebuilding beamlines, the experimental side, so the X-ray side of the house. The specific experimental subsystems, these include facilities and equipments, and not just for these beamlines, but we're trying to build out the facility. So much like the existing one, which was incrementally built and improved over 25 years, we're laying the foundation so that the APS, after the upgrade, again, continues to be a useful and incredibly useful facility for the next 3 decades. So it's, there are aspirational aspects to it, and we look forward to delivering those. If you visited the APS, you would see something like this today. Excuse me, sorry. There's a place called the Overlook at the APS, and basically the point here is this is a fully built out facility. What you see to the right of the picture, under the blue cabinets, are power supplies and diagnostics for the storage ring, which is directly below those cabinets. And underneath that, you see some yellow guardrails, and underneath that, you see a white wall, which sort of goes around like a ratchet all the way around. Outside of those walls, so the storage ring is directly under those blue cabinets, okay? There are shielding walls and things like this, because outside of this, it's safe for anybody to walk around on a normal basis. Outside of that, you start to see what we call hutches. So there's a blue door, it says BMA there. It's actually a 1, it's sector 1. It's a bending magnet beamline, and that is enclosure A. These are where the experiments are done, and so these are X-ray hutches. Now, at the heart of this, however, on the next slide, you'll see what we're replaced. So I've taken away the hutches, the experimental enclosures. The blue cabinets largely stay the same. And underneath in pictures is what the new storage ring will look like. And so this is what we need to install. And you saw a picture of the real thing just a few slides earlier. New storage ring is different than the existing ring in a few ways. It actually has more magnets in it. And where the current ring, this is a 40-fold symmetric machine, 1.1 kilometers around. And where the current ring, an electron would traverse 360 degrees. It sort of goes from the right side of this view graph to the left on the way around. So it's making a right-hand turn as you look from the top as you go. It would traverse 360 degrees. In the new machine, actually, it's a multi-bend achromat. And one of the things that does here is that we actually wiggle the beam both ways as it goes around. And so the total angle it curves is 435 degrees around as opposed to 360. We bend it both inwards and outwards. The great improvement in brightness comes from the size of the properties of the electron storage ring, or the electrons stored in the ring, excuse me, where the width, because of that change in the lattice, the width of the actual stored beam is much smaller than it was previously, such that the new beams will be about diameter of about 10 microns. So this is the finest human hair. And that decrease in the size of the beam and also the divergence of the beam is much more compact than the current machine, allows us to generate X-rays which are tuned for each beamline at a much brighter level than we currently do now. The other thing you see here is because we are trying to limit the downtime, we pre-assemble as much as possible outside of the ring before we start the downtime. So you see the magnets of various colors. The reds are dipoles, blues are quadrupoles, yellows are sextupoles. The purple ones are actually combination dipoles and quadrupoles. And you see underneath them, they're look like they're on sort of a raft. That's actually a large concrete base. And what we do in an offsite facility is we construct in advance all of the magnets on each one of those bases. So instead of having to install 1,321 magnets in the storage ring, actually we will install 200 of these sort of assemblies in the storage ring. So everything's pre-assembled, it's all pre-checked out, and we bring them in large assemblies weighing up to 55,000 pounds for assembly in the storage ring. The current project status by the numbers, here are lists of the thousands of components that we put in across here, and sort of the by dollar figure in DOE project terms about what our status is as far as cost and obligations, and the splits between the storage ring, the insertion device front ends, and the beamlines, which all relate to the generation of the X-rays and generating the actual science, okay? The obligations are contracts in place. Cost is when the actual material is received and accepted by us. In the storage ring, the largest single thing left to go is actually the labor to do the installation, for instance. Okay. A picture, the long beamline building, it has been a very interesting couple of years, as everybody knows, of course, between COVID and now with inflation, supply chain effects, There's war, of course. There's many things going on that have made things really a challenge over the past couple of years. And I know we aren't the only ones working our way through that. The long beamline building was completed in June of 2022 and is a large credit to our contractors and to the staff working on it. It was completed on time and on budget. You can sort of see the point here is 2 long beamlines with 2 large experimental areas at the end. This is complete. That portion's real. What's a little bit different is what's going on inside. The enclosure to the left, which will be Hexam, the high energy X-ray microscope, is largely complete. The one to the right is actually more like a concrete bunker, because the in situ nanoprobe, we look for the lowest vibration or interference with the experiment at all. So the enclosure there is actually made of concrete for thermal stability. It's got a relatively thick wall. It's actually on a 3-meter concrete base to limit vibration from ground motion. Illinois tends to be very quiet as far as earthquakes and so forth, but we also have a road that goes by, there's trains and things like that. So we do everything we can to isolate that. And so we're making the quietest possible environment in sector 19 there, the in situ nanoprobe. And the progress to the left of our contractor on the enclosures, the radiation enclosure, this is the Hexam enclosure a few weeks ago, actually. It's now complete. This is a massive enclosure relative to anything else you might see at the APS in the previous picture, for instance. This is a 2-story high enclosure. It's also at least 2 times as long as any other enclosure we have at the APS. And again, it gives the greatest flexibility for the long-term use of the Hexam facility over the next 30 years. So it was the time to build the infrastructure such that the scientific imagination isn't limited by what we construct now. So ongoing beamline preparation. So I just mentioned 20 IDE, that's Hexam. You see that picture there. But there are also other moves that we have to do at the facility, and this includes 8 ID. So I mentioned there are 40 sectors at the APS. Just for the purposes of this slide, we cleverly number each one. That's the sector it is. So 20 ID is sector 20, 8 ID is sector 8, 9 ID is sector 9, so on and so forth. ID is an insertion device beamline. We also have bending magnet beamlines. Those are noted with a BM. So you can see 8 ID and 9 ID we actually are removing. They have stopped operation of the beamlines now because we're completely rebuilding those beamlines with new facilities, serving largely, in some cases, the same community. In other places, we have to move them, and the community moves to a new location at the APS. So it's quite real, because we would not do this deconstruction if the rest of it wasn't coming along. We've actually delayed this due to supply chain effects over the past couple of years. We did delay the start of the shutdown about 10 months, a little over a year ago, just because of a buildup of supply chain issues. It's becoming real enough now that we have stopped these experimental facilities, these specific ones at 8 ID and 9 ID, and these user facilities. Because it's real and it's time to do this, we need to keep things moving along, but it's not a decision we take lightly, of course. We have a building with where we store everything. It's 100,000 square feet. It's one of the best rentals we've ever done. And these are just racks of new equipment. Everything has a QR code. Amazon would be proud. Everything has a QR code. Every shelf has a QR code. And so after something is received and accepted, we know where everything is and we know how to put everything together. And then to the right side on this slide, you see some of the magnet assembly things where we stage all the magnets as needed for a given raft, and then they are moved to a facility you can't quite see off to the right, where they put on those rafts and aligned to tolerances of better than 30 microns, magnet center to magnet center. And we're actually doing much better than that, but that's the tolerance we need. And we know that's reproducible over time. We also know that when we transport them, they won't move. We've done all the tests to prove that. So it's really been, it's gratifying. A year ago, these shelves were much emptier. So it's, our suppliers have been doing a great job over the past year, working through issues as we've all had. We've worked with them to do the best we can. This is actually a picture of one sector. It's 27 meters long. From the end right here in front of you, all the way down to the right-hand side. That's what one sector of the new machine will look like. And this is a test assembly done in our offsite facility to make sure everything went together right. And really, as a compliment to our engineering team, our design team, everybody who did it, it went together right the first time. We then took measurements to ensure everything was aligned properly, everything worked, and down to water lines. And so we're building up, we're practicing, but we also build up the confidence that this will go together correctly the first time when we put things in. So it's really gratifying to see the team do this. Looking forward, there's a downtime in the restart. We are a large user facility, one of the largest in the United States. And at the end of the day, this is a facility for the users. And so some of the users you'll see, I mentioned later, we have put together a map of beamlines at other facilities. Now there's not they'll have to ask for request beam time there, but the short version is we hold the delivery of a shutdown on the order of 12 months as critical. And so we have a detailed schedule that goes through this. You see the end of user operations, April 2023, and then we'll go to a phased restart in April 2024. Communication is critical. I'd ask anybody, we do have a web page, and I put out notes on a monthly basis and talk about our status. It's open to anybody. This is a public site. Anybody can get there. If we have a user who happens to be listening and would like to know about comparable beamline options, I include the link there. And these updates are also sent out monthly, and that's open. Anybody would like to hear from me on a monthly basis, please send a note to the email address there. In summary, we've made great progress over the past years safely. Our safety record is been great. And of course, there's been considerable challenges for all of us. I am fortunate enough to work with a great team, and I'm lucky to have them. And it's a real privilege. The risks and opportunities, come up daily. There's always something new, and we're working with our vendors to do the best we can. We're very excited about the time ahead, and we look forward to delivering the upgrade and the facility and bringing it back online for our users in 2024. Thank you very much. Any questions?
Thank you. And thank you very much, Jim. Great information there. I did have a question I'm curious about in terms of the construction. Have there been particular supply chain issue challenges, and perhaps even more in detail, who are the vendors, who are the suppliers of the particular equipment that you're needing to create with such specialized purposes?
Yeah, so thanks for the question, Dan. So we have an extensive supply chain network, and the vendors are too many to mention, to be honest. We basically act as our own general contractor, and have vendors overwhelmingly in Europe and the United States and Canada, who supply components to us. So for instance, for the magnets of the storage ring, just to pick on those, the magnets themselves, these are room temperature electromagnets. They're high tolerance, but there are a limited number of vendors in the world who typically build these things. And they're built to the specification of each facility. The Advanced Light Source Upgrade at Berkeley would have different magnets, similar functions, but they would be tuned to their footprint and things like this. They might go to the same vendor. So there's a limited number that we go to. We have best value contracts for each type of magnet with whoever won the bids. And then it's our job to manage those contracts. All of the vendors, magnets, whatever technical components, have seen supply chain issues. And one of the things the laboratory and our procurement department has done a great job on is actually doing everything we can to help the vendors. The last couple of years, there have been some straight delays. We do what we can to accommodate those delays by making our own changes internally to our schedules, such that we can juggle our work to accommodate that. Other times, vendors have discovered that subcontractors that they've worked with for years have gone out of business. They decided to retire. All sorts of things happen there, and so we are trying to help them find parallel subcontractors to do their sort of work. We're doing everything we can to help them, and I think the vendors have really been. Our industrial partners have really been outstanding. And I would say the single biggest thing we've learned is actually learning more from our vendors the more they tell us, the more we can help. And that's really the approach we try to take. So.
All right. Well, thank you very much for that overview and the connections that you had at the end of your presentation on how people can follow along, get monthly upgrades. I think the suggestions to the overall light source network that are other options for scientists to look to, that's very helpful. So we'll look to share that information again, both with this video, but also in some of our other communications, and help make sure that the scientists are aware of both what's coming and what the options might be. And lastly, I really like the way I jotted this down, that the flexibility, particularly of the hexam enclosure, is there to ensure that you're enabling and not limiting any scientific imagination as to what could be over the next decade or two. That's a fantastic mindset to have in this construction project.
Well, we certainly try. I'll admit there are some limits, of course. I do have a dollar figure to hit, but the goal, of course, is to, 2 orders of magnitude. It's an incredible change for any facility, and it's an incredible thing for an imagination, anybody's imagination, to think what you can do with 2 orders of magnitude. It's the difference between walking in an F-15 or something speed-wise. This is massive, right? So how do you imagine what you can do? So I look forward to reading about it and see what people come up with.
Nice. Yes, I could see that. That allows the scientists to really dream what could be possible without the sense of a technical limitation, perhaps, on that dream. That's great. Well, thank you again very much. And thanks, everyone, for joining this session as part of our 2022 annual meeting. We'll have another session coming up here very quickly.